Various Unix-like operating systems, including System V, Solaris, IRIX, and BSD, incorporate support for procfs. Linux expands its functionality to encompass non-process-related information, enabling a channel of interaction between kernel space. At boot time, it typically appears as /proc, acting as an intermediary to kernel-held details on active processes. Linux systems can leverage procfs to retrieve insights on the kernel and tweak specific parameters during runtime, such as sysctl adjustment. Notably, the GNU-PS utility utilizes the procfile system to gather process-related data without requiring specialized system calls. The Unix 8th edition introduced the /procfile system in 1984 through the work of Tom J. Killian. This innovative implementation aimed to replace the ptrace system call for process tracing, as documented in the proc4 manual page. The SVR3 operating system, first available internally at AT&T in 1986, initially lacked the /procfile system, but later included it in subsequent versions. However, the SVR3 iteration only featured files representing processes without the now common subdirectories. The special file system known as procfs, found in Unix-like operating systems, offers a structured view of system information and processes, significantly enhancing the accessibility of dynamic process data stored in the kernel compared to traditional methods. When SVR4 came into the picture, Roger Faulkner and Ron Gomez successfully ported the V8/proc to SVR4, leading to the publication of a notable paper at USENIX in January 1991. This version of procfs facilitated the development of tools like PS, accessible through functions like read, write, and I. Building on these foundations, Roger Faulkner further refined the /procfile system with the procfs2 interface for Solaris 2.6 between 1995 and 1996. Plan 9 took the concept even further by implementing a process file system that surpassed V8 by creating a hierarchy of separate files, integrating /proc into the file system structure. 4.4 BSD and its derivatives notably borrowed the /proc implementation from Plan 9. Over time, some operating systems started phasing out procfs for alternative solutions. FreeBSD, for instance, began transitioning away from procfs towards the sysctl interface by February 2011. To maintain compatibility with Linux user space programs, the FreeBSD kernel. On the other hand, procfs was removed from OpenBSD in version 5.7 in May 2015 due to lingering issues like race conditions that rendered it obsolete. In the macOS ecosystem, procfs was never implemented. User space programs had to rely on the sysctl interface for retrieving process data. Conversely, Solaris incorporated the /proc file system from its inception in June 1992, with later enhancements like procfs2 introduced in Solaris 2.6 in 1996 by Roger Faulkner. The /proc file system was introduced into Linux during version 0.97.3 in September 1992, with further expansion to include non-process-related data in version 0.98.6 by December of the same year. In current implementations as of 2020, Linux features a specific directory for every active process, even kernel processes, under directories labeled as /proc/PID, with PID representing the process number. Within each directory lies pertinent information regarding the individual process. For example, /proc/PID/CMD line pertains to the command that initiated the process, while /proc/PID/CWD is a symbolic link to the process's present working directory. Details on the environment variables affecting a process can be found in /proc/PID/environ. The file /proc/PID/exe is a symbolic link to the original executable file if it still exists, even if the executable has been deleted or substituted, as processes can persist post such changes. The /proc/PID/FD directory comprises symbolic links to each open file descriptor, whereas /proc/PID/FDinfo houses entries describing the attributes and state of each open file descriptor. The file /proc/PID/maps furnishes insights into mapped files and blocks, such as the heap and stack configuration. Accessible solely by a ptracing process, /proc/PID/mem holds a binary representation of the process's virtual memory. Furthermore, /proc/PID/root is a symbolic link to the root path as perceived by the process, commonly linking to / unless the process operates within a CRUT jail. Basic information concerning a process, including its operational state and memory usage, can be found in /proc/PID/status. Finally, the directory /proc/PID/task comprises hard links to any tasks initiated by the parent process. The PID, process ID, of a running process can be obtained using utilities like pgrep, pdof, or ps. For instance, to list all file descriptors of the most recently started Python 3 process, one could use the command ls l/proc/grep and python 3/fd. This /proc directory also contains system information not directly related to processes. In the 2.6 kernel, much of this non-process-related information was moved to a separate pseudo file system called cfs, mounted under /sys. For example, depending on the power management mode, directories like /proc, /acpi, or /proc, /apm may contain details about power management status. Other directories under e/proc include /proc/buddyinfo, which provides information on the buddy algorithm handling memory fragmentation, /proc/bus, representing various buses on the computer, e.g. in a PCI/USB, and /proc/FB listing available frame buffers. Details about the CPU, such as vendor, model, speed, cache size, and CPU flags, can be found in /proc/CPU-info. This file may also include a value for bogomips, derived from kernel timer calibration, but it is not a direct indicator of CPU speed and can vary significantly across CPU types, even at the same clock speeds. An example output from cat/proc/CPU-info shows processor information for AMD Athlon, a 2X2 270 processor with different clock speeds for two processors under Processor 0 and Processor 1. On multi-core CPUs, the fields siblings and CPU cores in /proc/CPU-info are used to calculate the number of hyperthreads and cores per CPU package. This calculation involves multiplying the hyperthreading, HT, per CPU package by the number of cores per CPU package for the siblings field, and just counting the number of cores per CPU package for the CPU cores field. By comparing these values, one can determine if a CPU package supports hyperthreading or is a dual-core system. When the values for a CPU package are equal, it indicates that hyperthreading is not supported. For instance, if a CPU package has siblings SIR2 and CPU cores MAMIN2, it is a dual-core CPU that does not support hyperthreading. Various files in the /proc directory provide information about the system, such as cryptographic modules in /proc/crypto, a list of devices in /proc/devices, and details about logical disk devices in /proc/diskstats. Additionally, /proc directories like /proc/interrupts, /proc/IO ports, and others offer insights into system resources usage. The /proc file system also contains vital data related to memory management, current load average, mounted devices, active swap partitions, network connections, and kernel modules, among others. The access to dynamically configurable kernel options in /proc/sys allows users to modify kernel settings on the fly, with directories representing different kernel areas and containing virtual files that can be read from and written to, affecting system behavior promptly. The /proc directory holds crucial system information and settings that are instrumental for system monitoring and configuration, with utilities like procfs in the procfs package providing tools to interact with this valuable resource.